Okay, we're going to look at some problems that will help you prepare for your quiz on sections 6.1 to 6.3. So what I would have you do is I would suggest that you try these problems on your own before you watch the solution on this video. That way you can kind of see if you got it right, if you prepare for the quiz. And then after each one of these questions, we'll give you a little practice problem to help you prepare. So the first one says, given f of x equals 3x minus 1 and g of x equals x plus 9, what is f of g of x? So remember, whatever comes second, that's what's getting plugged into the first one. So we're going to plug g into f. So whatever g of x is, which in this case is x plus 9, we will put that in everywhere there's an x in the f function, which is just one place. So f composed with g of x is going to be 3, but instead of the x now, I'm going to put the x plus 9, which is the g function, minus 1. Then I can distribute, so I'll get 3x plus 27 minus 1. Then 27 minus 1 is 26. So f composed with g of x is 3x plus 26. Number 2 is a very similar problem, where we're given f of x equals 7x squared plus 3 and g of x equals square root of x plus 9. Again, we have g second, so g is going to go in for f. So everywhere we see x in the f function, we're going to put g. So in this case, f composed with g of x, we have 7. Instead of x, which was there before, we'll have the square root of x plus 9 squared plus 3. So again, all this area that was just x is now where I put my other function in. So now the square root and the square will cancel. So that will just leave me 7 times x plus 9 plus 3. I'll distribute my 7. So that's 7x plus 63 plus 3, which is 7x plus 66. Okay, let's look at number 3. We have two functions, f and g. F is 2x minus 3, and g of x is x plus 2 plus 3 halves x. So what we want to do is see if these are inverse and back your answers up with work. So we know two functions are inverse. They're inverses if f composed with g of x is the same as g composed with f of x, so their composition's the same, and both compositions must leave just an x. So when I plug one function into the other, they both need to just have an x remaining. So if I do the f composed with g first, that means I'm putting g into f. I'm putting all of this function into the other function. So f composed with g of x will be 2 times x over 2 plus 3 over 2 minus 3. So wherever I had x in the f function, I put the g. I'll then distribute the 2. So 2 times x over 2 would be 2x over 2. If I multiply 2 times 3 halves, I'll get 6 halves minus 3. Well, 2x over 2 is just x. 6 over 2 is just 3 minus 3. So those 3's cancel out and leave me just x. So that is half of the information I need. So now I have to also show that g composed with f of x is also x. So in this case, I'll put f into g. So I'll take 2x plus 3 and put it in for that single x in the other one. So it was x plus 2, so now I'll write it 2x minus 3 divided by 2 plus 3 over 2. So I have these two terms that are divided by 2, so I can break it up as 2x over 2 minus 3 over 2, just dividing them both by that 2, and then plus 3 over 2. Well, 2 over 2 again is 1, and then we have negative 3 halves plus 3 halves, which will cancel, so we're left with just x. So this is sufficient to say f of x and g of x are inverses. Okay, let's look at number 4. If the point 5, negative 6 is on the graph of f of x, what point would have to lie on the graph of f inverse of x? So this problem really takes no work, because we know two graphs of inverses are symmetric to the line y equals x. So a function and its inverse are symmetric to y equals x. So when things are symmetric to the line y equals x, we know that the point that is on the other graph would just be the flip of that. So we know if 5, negative 6 is on the graph of x, then we know 6, negative 6, and 5 are on f inverse. So you just flip it. Okay, so this next problem, number 5, says, what is the inverse of h of x equals negative 3x minus 6? So to find an inverse, we will simply switch x and y and solve for y. Now, interestingly enough, in this problem, we have no y as it's currently constructed. But as we said earlier, h of x, any function notation just means y. So I can rewrite that as y equals negative 3x minus 6. So now if I want to find its inverse, I'll simply just switch x and y. So I'll put an x where the y is and a y where the x is. So now that we switched x and y, we will solve the equation for y. So I'll add 6 to both sides. So x plus 6 equals negative 3y. And then I'll just divide everything out by negative 3. So y equals x plus 6 over negative 3. So that's the inverse. So if we want to write it with inverse notation, we would just say it's h inverse x plus 6 over negative 3. Both are fine, but now this is the inverse of that function. If I wanted to test it, I could plug a number into my original. Let's say I plug in 1. If I put a 1 in for x, I have negative 3 minus 6, which is negative 9. So I put in 1 and I get out negative 9. So if the inverse works, if I put in negative 9, I should get back out 1. So if I put in negative 9 to my inverse, negative 9 plus 6 over negative 3 is negative 3 over negative 3, which is 1. So they are inverses because whatever I put into 1, the output of that entered in the inverse gets me back to the original. All right, number 6 talks about what is the domain and range of the function 4 times 3 to the x minus 2. So this is an exponential graph. So if you graph it on Desmos, that would be a good idea because you can kind of see what a graph looks like. But I know that the graph is going to look something like this. So the important part is you see where it flattens out. In this case, the graph should flatten out somewhere down here around negative 2. And I know that because everything that's important about the domain and range and asymptotes always is about this number that is added or subtracted to the end of the exponential. So I'm looking for the domain and range. So the domain of every exponential is always negative infinity to infinity. The range is always 0 to infinity unless we have a number added or subtracted to the end, which in this case we do. So instead of being 0 to infinity, we would shift it down 2, so it would be negative 2 to infinity. And if you look at your graph you produced, or this rough sketch I made over here, the graph starts basically at a y of negative 2 and then goes up forever. So that's why the range is negative 2 to infinity. We also want to know if there are any vertical or horizontal asymptotes. There are never any horizontal asymptotes for an exponential, so that would be none. And there's always a horizontal asymptote, and again, it is 0 unless there's a number added, subtracted, which in this case again is negative 2. So it's y equals negative 2. These two values should always match. The bottom of your range and your horizontal asymptote. Okay, now if you look at the last three problems, these are all from section 6.3 when we're solving these exponential equations with using the exponential law. Now the exponential law says if the two bases are the same, we can set the exponents equal. So in the first one we have that case where they both have a base of 4. This would be the best case scenario, so you would just take the exponents and set them equal. So the equation we would solve would just be x equal to 3x minus 6. Now we just use our basic fundamental algebra to solve these equations. So I would subtract 3x from both sides. So 1x minus 3x is negative 2x equals negative 6. And then I would divide both sides by negative 2. So x equals 3. If I wanted to check this, I certainly could. If I put it into the left side, I get 4 to the third, which is 64. If I put it in the right, I get 4 to the 3 times 3, which is 9 minus 6. But that's also 4 to the third, so that's also 64. So this does check out. Always a good idea on any equation to plug in your answer, see if it works. Okay, let's look at the next one. The problem with this one is they do not have the same base. This one has a 64, and this one has a 16. So our first goal is going to be to try to make those have the same base. So what I'm going to do is I'm going to take 64 and I'm going to factor it down. And I'm just going to take it all the way down to prime numbers. So 64 is 8 and 8. 8 is 4 and 2. Oh, there's a prime number. 4 and 2, there's another prime number. 4 is 2 and 2, so there's 2 more prime numbers. And 4 is 2 and 2. Those are 2 more prime numbers. So basically 64 is 6, 2, so it's 2 to the 6. And I just get this because I have 6 of the 2s circled. 16 is similar, and so we'll hope we can put it down to a bunch of 2s, which it will, because 16 is 4 and 4, which is 2 and 2, which is 2 and 2. So 16 is 4 2s. 2 times 2 times 2 times 2 is 16. So what I can do now is I will replace these new values into my equation. So instead of writing 64, I'll write 2 to the 6. And instead of writing 16, I'll write 2 to the 4th. So what you'll notice now is they have the same base. They both have the 2s, so we can just set our exponents equal. Now be careful, if you notice how I'll write this, it's 6, it's whatever's there, times the outside. So I'm going to make sure I put that in parentheses. May not even be a bad idea to put parentheses around your exponents originally, so you know you don't miss this step. And this is 4 times 2x plus 5, which we'll then go about trying to solve. So we have 6 times 3, which is 18x minus 6. And then we have 4 times 2, which is 8x plus 20. And so I'll just use my algebra to get everything on the same side. So I think I'll subtract 8x from both sides. That will give me 10x minus 6 equals 20. And again, I'm just doing fundamental algebra. Then I'll add 6 to both sides. So 10x equals 26. And then I'll divide 10 on both sides. So x is going to equal 26 over 10. Or if I reduce it, that's 13 over 5. When we get done with the quiz and we move on to sections 4 and 5 and 6, you'll see that the problem with exponential equations is when you can't get these bases to be the same. Like we got the 2's to be the same. If you can't do that, these become a little more difficult problem, which we'll have to have kind of a new methodology to go at. Okay, so this one we have a fraction, the 1/3, and then an 81. So if they are both fractions, I wouldn't try to flip it, but since this one is one fraction and one not, I will probably try to turn this fraction upside down. And if you recall, when we said that we turn a fraction upside down, 1/3 to say the first would be the same as 3 to the minus first. So we're just going to change that and have a minus 1. So I can change this as 3 to the minus 1, because I flipped it, and then have x plus 1 on that side. And 3 is a prime number, which is good. So now I'll try to break 81 down and try to make it a base of 3. So 81 is 9 times 9. And then both 9's are 3 and 3, 3 and 3. So 81 is 3 to the 4th, because there are 3 3's that multiply together to give me 81. So now I have the bases the same. One, I had to flip the fraction to get it to be the same base. And again, I just added that negative 1. So what I end up with is negative 1, parenthesis x plus 1 equals 4. So I'll distribute the negative 1. So negative x minus 1 equals 4. I will add 1 to both sides. So I get negative x equals 5. And then I'll divide both sides by negative 1. So x will equal negative 5. Okay, so hopefully you found this review helpful. If you have questions, please, of course, let us know. And good luck preparing for your quiz.